This is a common household light bulb. It's simple, yet brilliant. It was invented in the late 1800s, and amazingly, it has hardly changed at all. It works using a simple circuit, and the most important bit is the filament. It sits at the center of the bulb on a glass mount and is made up of a long, thin piece of tungsten metal which has an abnormally high melting temperature. Watch this slow-motion footage, which is 40 times slower than normal, and you can see the circuit in all its glory. When the bulb is connected to a power supply, the electrons travel along the circuit and continuously bump into the filament's atoms, causing them to vibrate. The atoms heat up to around 2,200 degrees Celsius, and boom, light. Who would have thought the humble bulb could be so ingenious?
The incandescent light bulb is a rather simple device. Its base has two metal contacts, which connect to a metal filament. The electric current's electrons collide with the atoms in the filament, making them vibrate. This energy heats the atoms to 2,200 degrees Celsius, at which temperature they emit visible light. The light bulb factory has two production lines that eventually merge. One prepares the glass bulb. The other makes the mount, the electrical components that go inside it. At the start of the mount line, a machine cuts glass tubing into pieces of specific lengths. The cut tubes land on what's called a glazing wheel that runs them through a gas flame for about 7 seconds. This heats the glass enough to smooth the surface. The glazed tubes now enter a flare-making machine, which heats each tube until the glass is malleable, then stretches one end into a flared shape. The next machine loads 2 copper lead wires into the flare end. Then it inserts a thin glass cylinder called the exhaust tube. A trip through a series of progressively hotter flames softens the tubes. A press then moves in to squash them, encasing the wires in glass. At the same time, the machine makes a tiny hole in the glass in between the wires. This is to later remove the air from inside the bulb. It'll exit via the exhaust tube through this hole. Next, the machine separates the lead wires and forms the ends into hooks. These fasten to a filament, a thin wire coil made of tungsten, a type of metal that holds up well to heat. The machine coats the lead wires in a liquid form of another metal, zirconium. This lengthens their lifespan by making them more resistant to moisture inside the bulb. Like the tubes, the bulbs are made of an inexpensive type of glass called soda lime glass. A machine stamps the top of each bulb with the voltage, the wattage, and the company logo. Opaque light bulbs are simply clear bulbs with an inside coating of synthetic silica, a white powder. The coating machine charges the bulbs to 30,000 volts. Combined with just the right amount of heat, this electrical charge makes a thin layer of powder cling to the glass. A series of flames evaporates the moisture and breaks off any impurities. As the two production lines merge, a bulb goes over each mount. Torches then fuse the flared end of the mount to the neck of the bulb. Arms move in and mold the neck to fit inside the bulb's aluminium base. The next machine vacuums out all the air in the bulb and replaces it with pressurized argon gas. This inert gas will resist heat buildup, helping the filament last longer. After bending the lead wires out of the way, torches melt and seal off the glass exhaust tube, locking the argon gas inside. The bulb would now be fully functional if connected to an electrical current, but it needs a base in order to screw it into the socket of a light fixture. The base is made of aluminium. This machine inserts one of the bulb's lead wires through the middle and solders it in place. It then spot welds the other wire to the side. The result? 2 base contacts to line up with 2 socket contacts. On their way to packaging, the bulbs undergo what's called flash testing, repeated light-ups using a higher voltage each time. This strengthens the filament inside, making it less likely to break during shipping. The bulbs are repeatedly tested. One last illumination to make sure nothing broke between flash testing and packaging. The automated packaging equipment handles the fragile bulbs with care. It's designed to have a light touch.
Inside this safety vacuum chamber, 12 volts of direct current electricity is applied to an ordinary piece of graphite pencil lead. Since there is little air to aid in combustion, the filament glows to a cherry red, and moisture from the clay that binds the graphite is boiled out of its matrix. By altering variables such as filament type, length, diameter, and input voltage, students of all ages can recreate the experiments that led to the creation of the first real light bulb. Finally, as you can see here, the filament glows hot enough to incandesce before it finally burns out.
Here's a fun prank you can make using an ordinary light bulb. First, find a couple of light bulbs. They can even be burned out, it doesn't matter. And using some work gloves, slowly twist the base of the light bulb back and forth until it loosens up. It might take some muscle, but you'll get it loose. Now there's a fairly good chance the bulb may break inside the base, so if that happens, just clean out the base thoroughly of all the old glue. Then grab light bulb number 2, and we're actually going to salvage the glass part. I picked at the brass base with an X-Acto knife until I got a small section I could grab with a pair of needle nose pliers, and then I slowly peeled the base back. Continue to do this until the bulb is freed from the base. Then you'll probably have to cut the small wire that's going from the filament to the center of the base. Now you've got your components, the base, and our intact light bulb. Then I picked up a couple of 2032 button cell batteries, and a white high-intensity LED. You'll want to stack the button cells and use a couple of zip ties to hold them together. Then you'll need 3 small pieces of wire. Solder one to the very end of the base. There should already be some solder there that you can use. Then solder the other one to the edge of the light bulb base. You'll also find some handy solder there ready to go. Then solder one piece of wire to the positive side of the LED. That's the longer leg. And solder the other side of the LED to the wire that's attached to the very bottom of the base. Then you'll wrap the lead that's soldered to the side of the base, in this case the black one, around the zip tie on the negative side of the batteries. And do the same with the wire coming from the positive LED lead. Wrap it around the zip tie and make contact with the positive side of the 2 batteries. Then take your battery pack and stick it in the base of the light bulb, and insert the LED in the small gutted out part of the light bulb, and then put it all back together. I used some hot glue to keep the base intact. Your mysterious light bulb prank is ready to go. Once you make contact with the side of the base and the bottom, the LED will light up. I just decided to use my ring to make contact, so when you hand it to someone, it won't light. And when they hand it back to you, you can make it light. This is the same kind of light bulb you'd buy in a magic shop or a catalog. And that's how to make your very own mysterious light bulb prank.
Did you know that mercury allows us to see in the dark? The production of fluorescent lamps is highly complex. The fabrication process starts with glass tubes that have been meticulously cleaned with warm water to remove dirt and impurities. Then the tubes have to be specifically shaped with the folder shaper. They're heated for 30 seconds, then quickly curved using a template. This automated machine can bend 14 tubes a minute. The bent tubes go into the coating chamber where a thin coat of phosphorus is applied to their inner surfaces. Phosphorus produces light by transforming ultraviolet photons generated by the ionization of mercury. The surplus phosphorus is removed from the ends of the tube to facilitate sealing. They now move to the electrical components. The cathode mount is made in this auto mount. Here they make the wire that will carry the current from the mount. The wire carrying the current is shaped. And here the wire is heated. This prepares it for the next step. It's essential to prevent the cathode coating from spreading to the prongs. The filaments are inserted into their mounts. The emissive substance plays a crucial role. When heated, it emits electrons, which participate in producing light. The emissive substance is actually this liquid. The wiring mount is transferred from the auto mount to the sealing machine. At this stage, the wiring mount and the glass tube are joined. Sealing is done at a very high temperature. One important step remains. This is where the glass tube is emptied of air and filled with gas. This machine also decarbonizes the tube and introduces the drop of mercury, essential for producing light. Once the very tiny drop of mercury is injected into the tube, the fluorescent lamp is almost completed. But one step remains. This threader positions the wires for insertion of the tube cap, which establishes electrical contact. The tube cap is placed into position in preparation for sealing. The cap must be securely attached and installed in a watertight manner to eliminate any risk of leaking. The capper permanently seals the cap onto the tube, and it's all finished. Each lamp is tested on a large testing wheel to verify its quality and performance. Once the meticulous inspection is over, the fluorescent lamps are carried to the packaging department. A robotic machine handles the lamps and places them into the packages. The glass tubes have now become fluorescent lamps.
Hi, I'm Maine's favorite light bulb.
Not for long, though, because I'm a CFL.
Canadian Football League, eh?
Nope, compact fluorescent light bulb.
Whoa, fancy name.
I use 75% less electricity, lasts 7 times longer, and I produce a lot less, gas.
Well,
Greenhouse gas.
Learn how cool new CFLs can save money and save the environment at efficiencymaine.com. Lighting the way to a brighter future.
Ah, the new kid CFL.
Yep, and you're that old-fashioned bulb.
I'm still the cheapest.
You get what you pay for. I save a household $50 during my lifetime.
But I hear they can never throw you out.
Exactly. I get recycled. You get... Is trash the right word?
You're still weird looking.
Is that your best shot?
Learn all the reasons why Mainers are replacing old-fashioned bulbs with CFLs at efficiencymain.com, lighting the way to a brighter future.
You CFLs may save money, last for years, and fight global warming.
Why, thank you.
But you're so limited. I hear you can't even work in a dimmer.
You haven't met my family.
Family?
Yep, there's a CFL for every socket in the house. 3-ways and dimmers, spotlights and vanities, even candelabras and bug lights.
Time for a nice long nap.
Check out special savings on CFLs right now from Efficiency Main, leading the way to a brighter future.
Don't forget, recycle all CFLs at stores displaying this sticker.
Welcome to CFL light bulbs in plain English. Here are two things that nobody wants to see increase: your power bill and pollution. Boo! We're going to show you a small step you can take that can turn these arrows the other way. Yay! We're focused on your friendly household light bulb, the incandescent kind. The chances are there's one within a few feet of you right now. Go ahead, look around. That light bulb is not cool anymore. It's the VCR of light bulbs, and it's quickly becoming obsolete, and for good reason. It's being replaced by a new kind of bulb. It's called a compact fluorescent, or CFL, and it's an easy way for you to make a big difference. Here are two reasons why. The real problem is coal, which is used to create over 50% of our electricity. When you turn on a light bulb, most of the electricity that powers that bulb comes from burning coal. When it's burned in power plants, CO2 and other pollution is released into the air. More burning coal equals more pollution. Not cool at all. If that wasn't enough, coal also costs money. The more you burn for electricity, the higher your power bill. So the ultimate goal is to burn less coal by using less electricity. Here's why new light bulbs matter. If you replace that old light bulb with a new CFL, you can save money and help prevent pollution at the same time. Consider these 3 big points. First, let's say you have a lamp in your house that you leave on for 1 full year, 24/7. You start with a 750-hour incandescent bulb. That lasts about a month. This means that over a year, you'll use about 12 bulbs for the lamp. At 60 cents a bulb, that's about $7.20. Now compare that to a single CFL that costs about $4. A CFL in the exact same lamp will last 10,000 hours. That's about the same as 13 regular light bulbs. This should be clear. Less hassle, less money. But the last 2 points are the big ones. Lighting accounts for, on average, about $20 of a $100 monthly power bill. And CFLs use 1/4 of the power compared to an incandescent bulb. This means that using CFLs can lower a $100 power bill to $85 a month. That's cool. And finally, switching to CFLs can prevent hundreds of pounds of CO2 pollution each year. That pollution is a cause of global warming. So you can see the point. CFLs are simply a smarter way to light your home. If you're still not convinced, note that these aren't the buzzing blue tube lights from the kitchen of your past. CFLs have come a long way lately. Popular Mechanics did a blinded study with new CFLs, and participants preferred the CFL light compared to incandescent bulbs, and they fit in the same fixtures. We should mention that CFL light bulbs contain a bit of mercury and should be recycled or disposed of properly. The question to ask is, why not switch to CFLs? The next time you're at the store, pick up a 4-pack of CFLs and replace the bulbs that are on the most, maybe the porch lights. Then ask your friends, why haven't you switched? Are you still watching movies with a VCR? I'm Lee Lefevre, and this has been CFL Light Bulbs in plain English.
What's the difference between this bulb, the traditional incandescent light bulb invented by Thomas Edison over 120 years ago, and this bulb, the compact fluorescent light, or CFL bulb? This 60-watt traditional incandescent light bulb is very energy inefficient, since most of the power consumed by the bulb is radiated out in the form of heat. Compared to compact fluorescent light bulbs, which use only 25% of the energy consumed by the traditional incandescent light. In addition to the energy savings of a compact fluorescent light bulb, there are other benefits. Compact fluorescent light bulbs produce the same level of light as the traditional incandescent light bulb. They also last 5 to 10 times longer than traditional incandescent light bulbs. So while CFL bulbs may be initially more expensive to purchase, they save you money in two ways. They save you money on lower utility bills month over month and fewer bulbs purchased to replace the traditional incandescent light bulbs that burn out. Together, these two factors help reduce greenhouse gases, which are produced by power plants that would otherwise be producing power for this 60-watt bulb, but instead are producing power for this 13-watt bulb.
New energy-efficient, compact fluorescent and LED light bulbs have been all over the media lately. Seems like every time you turn on the news or go online, you hear or read about the number of power plants that won't have to be built if everyone swapped out a few bulbs. You may have also heard that Walmart is implementing a new marketing strategy for compact fluorescents and plans to sell 100 million by 2008. One California lawmaker even believes enough in the new bulbs that he has proposed banning incandescent light bulbs in California by 2012. But how efficient are these new bulbs? We at Alternative E have decided to figure it out by examining 3 different bulbs: a standard 60-watt incandescent, a compact fluorescent 60-watt equivalent, and an LED light bulb. To understand how efficient these new light bulbs are, we need to evaluate how much power they use. And to understand electric power, we need to make a short trip through high school physics. Electric power is the amount of energy transferred per unit of time and is measured in watts. The wattage of a light bulb is calculated by multiplying the voltage of the power source, which is measured in volts, and the current going through the light bulb, which is measured in amps. To examine these light bulbs, we built a device that will let us measure both the voltage of the power source and the current through the light bulbs. The device begins with a standard 110 volt plug, which leads into a switch. From the switch, the electricity is moved from the wires onto rails which allow the voltage and current to be measured. The white, neutral wire is attached to a solid rail, while the black, hot wire is attached to a split rail that allows the current through the light bulb to be measured. At the other end of the rails, the electricity moves back onto wires and into a simple light socket. Please note that this testing device is inherently dangerous. The electricity traveling through the exposed rails creates a high risk of electrocution if not handled properly, and there's a risk of burns from the light bulbs. We also need a multimeter to measure the voltage and current. However, it must be one that can measure AC voltage and AC current. To measure the voltage, we start with the device unplugged and the switch in the off position. We then place the multimeter in AC voltage mode and place the common probe in the neutral rail and the voltage probe in the hot rail, effectively putting it in parallel with the light socket. The device can then be plugged in. You'll notice that even with the device turned off, we're measuring a small voltage. This is a phantom voltage, likely due to electromagnetic interference or coupling, which shouldn't be a problem. When the device is turned on, you'll see the voltage jump significantly. If we zoom in on the multimeter, you can see that when the testing device was turned on, the voltage jumped from about 7 volts to 124.5. A voltage of 124.5 should be consistent for all 3 light bulbs, so we'll go ahead and enter it in the data table. To measure the current through each light bulb, we have to change the position of the multimeter. Now the multimeter is put in series with the socket, with one probe placed in the hot rail coming from the switch and the other probe placed in the hot rail going to the socket. After the probes are placed, the multimeter can be set to measure AC current. Now we're ready to begin testing the light bulbs. We begin by placing a normal 60-watt incandescent bulb in the socket. The measurement from this bulb will give us a comparison point for the other bulbs. After we flip the power switch, we see the multimeter jump to 0.505 amps and hold steady. We add the current measurement to the data table and calculate the power usage of the bulb at 62.87 watts, which is pretty close to where it should be. Now we'll take out the incandescent bulb and put in a compact fluorescent that's sold as a replacement for the 60-watt incandescent bulb. When the compact fluorescent bulb is initially powered up, it measures in at 1/10 of an amp, but you'll see that over a few minutes it increases and settles in at 0.112 amps. Entering 0.112 amps into our data table gives us a power usage of 13.94 watts, meaning that the compact fluorescent uses 75% less energy than the standard light bulb, or, put another way, is at least 4 times more efficient. Lastly, we remove the compact fluorescent bulb and put in an LED light bulb. When we apply power to this bulb, you can see that the current measurement immediately jumps up to 0.03 amps and holds. After we enter the LED current into the table, we calculate that the LED bulb has a power usage of 3.74 watts, making it vastly superior to both the standard incandescent bulb and the compact fluorescent. Through our experiment, I hope you've gotten a better idea of the efficiency of some of these new light bulbs. However, we should point out one difference between the compact fluorescent and LED light bulb in terms of light output. A standard 60-watt incandescent light bulb has an output of approximately 850 lumens, and the compact fluorescent replacement has an output of 800 lumens, so it really can be swapped out with a standard incandescent in many situations. However, the LED light bulb only has an output of 60 lumens, and it was the highest output bulb we could find without going to a floodlight. So while the LED light bulbs use significantly less energy than other bulbs, they are not suitable for every application yet. This video was produced by AlternativeE.org, an alternative and renewable energy website where all news and information is submitted and ranked by users like you.
Incandescent lights have been described as heaters that give off a little light. This bulb, for example, pumps 75 watts through a wire whose electrical resistance makes it glow white hot. This is very inefficient. This fluorescent bulb uses only 13 watts to excite a gas that glows with much greater efficiency. The downsides, however, were poor light quality, poor aesthetics, and an annoying flicker when it was turned on. For this reason, many people still prefer using incandescent floods, despite the greater long-term costs to both home and environment. Recent technological improvements, however, have produced flicker-free, instant-on compact fluorescents with markedly more attractive designs and the same warm color temperature as incandescents. Floodlight versions of these CFLs are now available everywhere, giving the same advantages of incandescents with none of the disadvantages. This comparison shows a 75-watt incandescent on the left with a 25-watt fluorescent on the right. Notice they both go on at the same time, and the fluorescent, consuming only 1/3 the energy, is markedly brighter. In addition, today's 1100 lumen CFLs can last 15,000 hours, up to 10 times longer than similar incandescents, and can pay for themselves in no time.
Looking for the next CFL, or at least the next emerging technology that can revolutionize energy efficiency the way CFLs have. That was the goal of a unique side-by-side comparison done by the Bonneville Power Administration, where we tested LED lighting with other types of lighting for energy efficiency and consumer reaction around the region. I'm Katie Pruder at the BPA headquarters, one of the test sites. Can you tell the difference between this and this?
So here we have an example of both the LED and the CFL lights, and on this side of the picture is LED. As you notice, the light is more focused. And as we move across here, this is a CFL, and you can see the light is more diffuse.
LEDs, or light-emitting diodes, are small light sources that become illuminated by the movement of electrons through a semiconductor material. Popular in holiday lighting and other specialty uses, LEDs are durable, long-lasting, and use about 1/10 as much energy as incandescent bulbs. BPA is testing consumer reaction to a much broader use of LED lighting with a pilot project involving 12 utilities and their customers. For about a month, half of the lighting at each participant's location was replaced with LED lighting. Through comment cards, employees and customers provided feedback about the quality of LED light compared to the traditional lighting. The St. Helens Library, served by Columbia River People's Utility District, was a participant, and they ended up with some interesting results. What do you think about these LED lights?
Well, I'm really thrilled to have them here in the library. When I first started working here, I would turn the switch on for these particular lights, and it would very quickly get too hot to work up here at the front desk, particularly in the summer. It was unfortunate to not be able to use them. So that now that we have these new LED lights, side-by-side comparison with our old lights, we can see the difference, and the heat generation between the two is really quite markedly different.
Less heat output is only one of many benefits from LED lights.
Energy efficiency is considered to be a resource to the utility, and it's actually the least cost or cheapest energy resource. So if we can get people to use energy as efficiently as possible, in homes and businesses, that just means we can prolong the date when we have to go out and find new generation sources, which would be more expensive and have more impact on the environment.
As you can see, early results show the LEDs have performed well in most applications of the test, and public feedback was mostly positive. So are LEDs the next CFL? Maybe. BPA believes in the technology enough to continue researching it and making sure LEDs are used in appropriate applications for cost-effective regional energy efficiency savings. For more information, check out BPA's website at www.bpa.gov.
People are fascinated by light. I mean, just glancing over at a display of flashing lights can grab my attention. Do you ever remember sitting around a campfire, staring at the flames, and just being totally transfixed? Almost like if you're watching TV. It's comforting, and it can even be hypnotic. Recently, technology has made creating light a whole lot easier to do. For that, we have this little guy to thank. The light-emitting diode, or LED for short. LEDs have a lot of different uses, from a simple power-on indicator to traffic signals. LEDs use about 10% of the energy of a traditional light bulb, and they can last about 30 times longer. That makes them a pretty big hit with businesses looking to do large-scale visual communication. The first person to ever report the effects of a light-emitting diode was researching another form of communication. In 1907, a man by the name of H.J. Round was researching radio waves for Marconi Labs. He was using a device called a cat's whisker detector, which, no, does not contain any cats or part of cats. Round was searching for a sweet spot on a crystal of silicon carbide when he noticed something odd. Part of the crystal started to glow. It lit up a pale yellow. And that was an LED. H.J. Round's crystal experiment was so cool and simple that I had to try it myself. So I got a piece of silicon carbide. Then I hooked that up to the positive lead on my power supply with an alligator clip. I hooked a little sewing needle to the ground on my power supply. And then I began to search for light emitting zones. I built my own sort of cat's whisker detector in order to keep the needle in place on a particularly bright spot I found. Now I can sit back and enjoy the warm glow of a homemade LED anytime I choose, even though it's pretty dim, but it's still cool. As far as we know, Round's research into light-emitting crystals ended here, which is a shame because he was definitely onto something. But of course, that's not the end of the story. 15 years later, in Imperial Russia, a scientist and inventor named Oleg Vladimirovich Losev noticed that certain diodes in radios started to glow a bit when in use. Losev conducted a lot of heavy research and published his findings in several languages, but sadly, they seem to have gone unnoticed. It wasn't until 1962 that a visible light-emitting diode was made practical by Nick Holoniak, working at General Electric. He's widely known as the father of the LED. The technology that Holoniak brought to the public is remarkably similar to our crystal experiment. A thin metal wire connects one side of the circuit to a small piece of semiconductive material on the other side. The LED's two leads are cut to different lengths to show you how it should be connected. The longer one is called the anode, and that connects to positive. And the shorter is the cathode, and that goes to negative. To power an LED, you can just use a simple coin cell. This is a CR2032. Then just make sure the longer lead is on the positive side, which is wider and smoother, and the negative is on the other. If you plan to use a battery, let's say a 9 volt, you'll also need a resistor to limit the current so that we don't burn out the LED. Connect negative to the cathode, the shorter lead, and we'll put a 470 ohm resistor between the positive battery and the anode. For more useful info, check out the LED Center, and there's a lot of great history at the LED Museum. For all types of project ideas, info, and inspiration, head over to makezine.com.
Hey, what's up everyone? Today I'm going to be showing you guys how to wire an LED. This fun and somewhat easy to do project is great for anything electronics and can be used virtually for anything as long as there's a power supply. First, what you'll need is resistors to resist your current, a soldering gun, solder for your soldering gun, scissors to cut your wire and or strip the wire, LED holders is optional, your LEDs, make sure if you get more than one they're all the same. For this video, to test the LED, I'm going to be using a 6-volt lantern battery, and for the wires I'm just going to use a black wire for negative and the red wire for the positive. Alright, let's get started. Okay, so what you see here is what we're going to be working with first. As you can tell, I've already cut my wires and stripped them at the ends, so they're already pretty much ready to go. What you want to make sure is when you get your pack of resistors, in order to determine what resistor you need, you're going to first need to know what LED you're going to be getting. And so what I would do is save your package that your LED came in. It should look like this. If you flip it over, it tells you everything you need to know on the back. And so that's very important. Make sure you keep your bag. And to determine that, go to metqmods.com. It has a very good LED calculator on it. And just plug the information in off your package and for your LED, and that would determine what resistor you need. Now for this one, mine's a little overkill, but it's always better to go over the recommended resistor than to go under, otherwise you'll burn it out within seconds. I mean, LED won't last very long at all, so yeah, make sure you do that. Okay, so we got our positive wire here, but before you start you're soldering up your LED and resistors, you gotta know which side of the LED is positive, which side is negative. So to determine that, if you look closely, let it focus, there we go. The negative side of the LED leg is shorter than the other. See that? So the shorter side is the negative lead and the longer side is the positive lead. You could tell inside the LED the lead is also fatter. The negative lead side is also fatter than the positive. Okay, so now what I also did was I also cut my resistor shorter, just because we don't need a very long resistor for this. Now you could do this one of two ways. You could solder your resistor first to your LED and then to a wire, or you could why aren't you focusing? Okay, you could first solder it to your positive side first and then to a wire, or you could hook it up to a wire and then solder the wire to the positive side. Whichever way, doesn't matter. I'm gonna just solder the resistor right to the positive side for you. Okay, so now we're ready to solder the resistor to the LED. First, before we do that, I like to hold the reel with the with the solder sticking out of it for control and stability, instead of just holding the wire like that. Also, if you guys never done this before, I highly recommend practicing on like a couple of wires or so until you feel comfortable enough. Now this could be done in one of two ways. One way, you could hold the solder down where you're going to solder and use the gun to melt the solder on it, or you could just gently touch the tip of the gun with the solder, and so you can see it's melting it onto the tip. So all you have to do really is just touch the connection and it should solder. Okay, so let's get started here. And just gently break away from it, and the solder should jump off from the tip onto the wire, and solder them together. Let's check that out. Alright, there we go. We got the resistor soldered to the positive lead right there. Alright. Okay, now once you solder your resistor to your positive leg, this step becomes a little easier now that all you have to do is solder the wires to your leads and your resistor. And one way, what I like to do is I like to twist the wire around the legs. This makes it, a lot more secure and easier to solder up. So yeah, do that and just solder, just like how you saw me do on this one, do to these two right here. Alright, so once you got that soldered, should look something like this. It doesn't have to be perfect, as long just give each side a little tug, and if it's secure enough, then you're fine. What I would do too is wrap the solder points and actually the whole wire that's exposed, with electrical tape, so nothing shorts out, and you'll be fine. Alright, so once you got them soldered, what I would do is test the LED and make sure your connections are secure. And as we see here, lights up pretty nice. This thing's really bright. Yeah, it works good. Alright, so now all you have to do is solder your leads to whatever power source you're going to be putting this in. And for all you computer guys out there, a cool trick is if you got an old fan laying around that you're not using, that's a Molex, has a Molex connector on it, just cut the wire off the fan, and bam, you got your leads right there. Just solder, all you'd have to do is solder your LED to the black and red wire, and all you gotta do is plug your Molex connector into a Molex plug, and it should work. Alright. Thanks for watching, guys. Please comment, rate, subscribe. If you have any questions, just leave a comment or send me a PM. Thank you.
We're getting there. We're getting there. Well, that's better, that's better, that's better. That's more like it now. Stand there. I'm sure some of them are Pong, but... Right, I'm aiming for that snake over there, yeah? Stay there. Good. There are two in front of you, and move those to the right. Let's go on there. This one here. Everybody stop there. Don't move. Start on the next page. Yes, that's better. That's good. That's good. Looking good. Get away! That's it.